So titrations are often used in acid-base reactions. They're not specific to acid-base reaction, but a titration is a common laboratory method that's used to quantitatively determine the concentration of an unknown solution. So this is not limited to acid-base reactions, but it's often used in acid-base reactions. The titrant, or a solution of a known concentration, is slowly added to a known volume of the analyte, where the analyte is a solution of unknown concentration, and you slowly add the titrant until the reaction reaches its equivalence point. The equivalence point is the point at which enough titrant has been added to react with all the analyte without any leftover reagents. So there's no extras present. This requires that you know what you're measuring. It requires a reaction of known stoichiometry. Okay, so for example, we have an acid-base reaction. This reaction has a known stoichiometry. We know that there's 1 hydrochloric acid for every 1 sodium hydroxide. And we know what is in our analyte. We know there is HCl in the flask to begin with. So we're going to add hydroxide slowly until we react with all of the hydrogen ions until there's no hydrogen ions left over. So I'm going to add hydroxide every time a hydroxide falls into my flask. Then it's going to react with a hydrogen ion and make a water molecule, right? And I'm going to do that until all of the excess hydrogen ions have been consumed in this reaction, and I've created all water. So now I don't have any HCl left. I don't have any sodium hydroxide extra. I just have liquid water and sodium chloride ions. Okay, so I start with an acidic solution in the flask. My pH is less than 7 because I have an acidic solution. I have a known volume of analyte, so I've put in 25 mils here, or however much that I know that I've put in. And I have an unknown concentration of the analyte. So I have an HCl solution. I know it's HCl. I know I have 25 milliliters of it, but I do not know what concentration it is. I add base until it is completely neutralized without excess, so there's no excess hydrogen ions and there are no excess hydroxide ions. It's all turned into water and salt. I measure the volume of the titrant that was required to get to that point, and I know the concentration of the titrant. And so now we can do that stoichiometry process to determine what is the concentration of the acid. So the calculation is exactly what was covered in the previous video. We use the known concentration and the volume of the titrant added to determine the moles of titrant used in the reaction. We find the volume of titrant added from the burette. Okay, so the burette actually has lines on it. It starts at 0 at the top and it goes down to 50. That's the size of the burette we'll be using. And so how much volume of titrant that you add, or the volume of hydroxide that you add, would be the final volume minus the initial volume to give you the volume added. You use the concentration of the titrant then to find the moles of titrant, and then use the mole ratio from the balanced chemical equation to convert moles of titrant into moles of analyte. And then you use the moles of analyte and the volume of the analyte that you started with to find the concentration of the analyte. So we can walk through this set of calculations. If I used 10.73 milliliters of 0.1 molar NaOH to titrate 25 milliliters of an HCl solution, what was the initial concentration of the HCl? Well, I start with what I'm given, the amount of NaOH that's used. So I have my concentration times the volume in liters. My units are going to cancel for liters. I'm going to end up with moles of sodium hydroxide. I'm going to use that mole-to-mole conversion factor from the balanced chemical equation, 1 mole of HCl for every 1 mole of NaOH. And again, NaOH is in the denominator so that I can cancel my moles of NaOH and have moles of hydrochloric acid left over. And then I can use my moles of hydrochloric acid and my volume of hydrochloric acid to determine the molarity, or the concentration of hydrochloric acid. Now, on the previous slide, when we got to that equivalence point, the flask was pink. So how do we know that we have gotten to the equivalence point? We need some kind of indicator. So we use colored indicators when we do titrations. There are other ways to do it. We can monitor the pH of the solution as well. But in this lab, we'll just be using acid-base indicators. Indicators for acid-base reactions are themselves acids or bases. They change color depending on what the molecular form they are in. So the color change depends on the pH of the solution. So phenolphthalein is a really common indicator, and we'll be using it in lab this week. When it's in an acidic environment, you have a lot of excess hydrogen ions present in solution. And so the phenolphthalein molecule has its hydrogen ions attached to it, okay? And the structure of this molecule is such that it's colorless. It actually absorbs light in the UV region. When you put it in a basic environment, so there's a lot of excess hydroxide ions, the hydroxide ions will actually pull the hydrogen ions off of the phenolphthalein molecule and leave them, right? So this is a -2 now. This molecule is an ion, and it's changed in the bonding. If you specifically look at this carbon in the center, this has four single bonds, and now it has 2 single bonds and 1 double bond, and that is called a more conjugated molecule. So this molecule, the anion, the dianion, is basic, or it's pink, right? So when you have it in an acidic solution, it looks colorless because it's actually absorbing UV radiation. And as you go to a higher pH, right, you strip those hydrogen ions off of the molecule and it turns pink. Phenolphthalein will turn pink around 8.2 is where it starts to turn pink. So 7 is colorless, 9 it's just slightly pink, and if you go past that, it is bright, bright fuchsia. So other indicators that you might run across, methyl red, it goes from a nice pink red color to a yellow color across the span of pHs. Bromocresol green is the same. You go from a yellow to a blue, and so you have like a green sort of in the middle. And here's the molecular forms and how they change in acid-base environments. So if you want to choose an indicator, you have to choose an appropriate one for the experiment that you're doing. So first you would consider the pH of the solution at the equivalence point. So you choose an indicator that'll change color very close to that pH. Now in the reactions that we've been looking at for HCl plus NaOH, the products of that are water and salt. And sodium chloride, sodium ions and chloride ions do not have any acid-base character. So once you have completely neutralized the acid with the base, you should have a pH of 7. Okay, so we would look at a color chart like this, and we would try to figure out which indicator will change color around a pH of 7. So we'll go to pH of 7, we'll come down here, we see that alizarin will turn from a yellow to a red around pH of 7. Bromothymol blue will turn from a yellow to a blue around a pH of 7. Phenol red goes from yellow to red. Nitrophenol, a couple of other things. Phenolphthalein is kind of up here. Seems like it's a little out of the range. If there's more than one choice, so say we're trying to decide between alizarin and bromothymol blue, right? We would then consider how easy or hard it will be to visually determine the change in color. So is it going to be easier to see the difference between, let's see, we would be looking for the disappearance of green here, right? So like going from a green to a blue, or would it be easier to see phenol red, which would go from yellow, 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 and then it would just start to turn orange, right? Would we be able to see that change in color? That's the question. So what we might choose for our experiment is phenolphthalein is used a lot. We saw that the color change happens a little higher in pH than maybe bromothymol blue might be more appropriate. This plot is showing how the pH changes from a pure HCl solution, and then you start adding NaOH, and you add NaOH, and your hydrogen ion concentration will start to decrease because you're turning it into water. At the equivalence point, you should have a pH of 7 because all that's there is water and salt. You don't have any excess hydrogen ions and you don't have any excess hydroxide ions. And if you add more NaOH after the equivalence point, it's going to make the pH rise. Okay, so you'll have a basic solution because you've added extra NaOH. So we want something that's going to change color there. Now bromothymol blue right here will change from a yellow to a blue right around pH of 7. Would you be able to see the difference between this green color and the blue color to just know the disappearance of all the green? That might be hard to distinguish between the green and the blue. Phenolphthalein, even though it starts to change color a little higher pH, it is very, very clear to see the difference between colorless and pink. We can detect very slight variations in that color as the pink starts to come in, even with just our eyes. And so we're going to use phenolphthalein and watch for that change from colorless or clear liquid into a pink liquid. Okay. This means that the endpoint that's given by the color change of the indicator, so where the indicator changes color, that is actually different than the equivalence point. Okay, so ideally we would have an indicator that would match really well with our equivalence point, but it might not always be feasible. In this case, phenolphthalein will be using phenolphthalein, and therefore the endpoint given by the indicator is not the equivalence point from the stoichiometric reaction. So there is error associated with using an indicator that is not going to change colors at the equivalence point. However, the error in the volume of NaOH dispensed is very small. So what we see here is that the range of volumes that would be required, right, to go from colorless to pink, right? So if I'm following this volume, 20 milliliters, I'm colorless, right? 24 milliliters, I'm colorless. 25 milliliters, I'm colorless. I add one extra drop. I'm still like just barely at 25 mils here. I add one extra drop and all of a sudden I'm fuchsia. Okay. So the error in the volume dispensed is very, very small for an indicator like this because it's on this sharpest ascent in the curve here. Okay. So there is some error, some indicator error, caused by the fact that phenolphthalein will change colors at a higher pH than the equivalence point, but the error is very small. So what we will be looking for in lab, okay, this is what you're going to start with, a completely clear solution. Even when you put the indicator in, it should turn clear. Okay, as you start to dispense NaOH into your flask, you're swirling, the swirling should make the pink go away. And when you first start to see that it's going to be permanent pink, you're going to stop, you're going to slow way down, and you just want the faintest pink that you can find here. If you add too much, you add one more drop after that, it's going to turn really bright fuchsia. And I promise you somebody in your lab will do this and you'll be able to see that pretty color.